Welcome! In this session, we'll be exploring problem number 1833, maximum ice cream bars. This is a fascinating problem where we aim to maximize the number of items purchased within a given budget. Stay tuned as we break it down step by step and uncover the best approach to solve it. Imagine you are at a store that sells n different ice cream bars. Each bar has a specific price, which is provided in an array called costs. The ith element of this array, costs, I, represents the price of the ith ice cream bar. Now, you have a limited budget, represented by the variable coins. Your goal is to maximize the number of ice cream bars you can purchase with this budget. If you can't afford to buy any ice cream bars, the result should simply be 0. The problem asks us to return the maximum number of ice cream bars that can be bought given these constraints. To better understand the problem, let's consider the input and output formats. The input includes the array costs and the integer coins. The output will be a single integer, representing the maximum number of bars you can afford. Let's look at some examples to clarify this further. In the first example, the input array of prices is 1, 3, 2, 4, 1, and the budget is 7 coins. To maximize the number of ice cream bars, we can pick the bars with prices 1, 1, 2, 3. Adding these prices together gives us a total cost of 7, which matches our budget exactly. Since we used all our coins and bought 4 bars, the output is 4. In contrast, for the second example, the array of prices is 10, 6, 8, 7, 7, 8, and the budget is only 5 coins. Here, all the bars are too expensive, as every price in the list exceeds the budget. This means we cannot purchase any ice cream bars, and the output is 0. Now, in the third example, the array of prices is 1, 6, 3, 1, 2, 5, and the budget is 20 coins. Since the total cost of all the bars is 1 plus 6 plus 3 plus 1 plus 2 plus 5 equals 18, which is less than the available budget, we can afford to buy all the bars. As a result, the output is 6, because we were able to purchase all 6 ice cream bars. This demonstrates how we aim to maximize the number of bars purchased while staying within the budget. Finally, let's consider the constraints and edge cases. The number of ice cream bars, n, can range from 1 to 100,000, while the price of each bar and the total number of coins can go up to 100,000 and 1 billion, respectively. For edge cases, if your budget is smaller than the cheapest bar, the result will always be 0. On the other hand, if the budget is very large, you can afford to buy all the bars. If there's only one bar, whether you can purchase it depends solely on whether its price is within the budget. Similarly, if all prices are identical, the solution will depend on how many bars fit within the budget. These constraints and edge cases help us better understand the problem and prepare for various scenarios during implementation. To tackle the maximum ice cream bars problem, our goal is to buy as many ice cream bars as possible without exceeding the given budget. This requires a strategy that prioritizes the cheapest bars first, as this ensures we maximize the quantity we can afford. One approach we considered is the brute force method. The intuition here is straightforward: repeatedly identify and purchase the cheapest bar at each step until the budget is insufficient. The process involves iterating through the array, sorting it to find the least expensive bar, deducting its cost, and continuing until no more bars can be bought. However, this approach is inefficient because sorting the array repeatedly increases the time complexity to n squared, making it impractical for larger datasets. A better alternative is the optimized approach using a greedy strategy. By sorting the array just once, we can systematically buy the cheapest items in a single linear pass. This significantly reduces redundant computations and improves performance. In the optimized greedy approach, we begin by sorting the array of costs in ascending order. Once sorted, we iterate through the array, purchasing bars one by one as long as the budget allows. For each bar we buy, we increment a counter and deduct the bar's cost from the remaining budget. The process stops as soon as the budget becomes insufficient to afford the next bar, and we return the total count of bars purchased. This method has a time complexity of n log n due to the initial sorting step, followed by a linear n iteration over the array. One of the main advantages of this approach is its efficiency. It ensures optimal results while avoiding redundant operations. However, sorting the entire array might still feel excessive in scenarios where the budget only allows for the purchase of a few bars. For these cases, we explored an alternative approach using counting sort. The counting sort approach is particularly useful when the range of costs is small. Instead of sorting the array, we create a frequency array that tracks how often each cost value appears. Then, we iterate through this frequency array from the smallest to the largest cost, purchasing as many bars as possible for each cost until the budget is exhausted. This eliminates the need for a traditional sorting step, reducing the time complexity to O, n plus k, where k represents the range of costs. While this approach is faster than sorting when the range is small, it has a drawback. If the range of costs is significantly larger than the number of bars, it can lead to high memory usage, making it impractical. After weighing the options, we chose the optimized greedy approach with sorting as our primary strategy. The key insight here is that sorting the costs array once provides a clear path to an optimal solution without the additional complexity or constraints of the counting sort method. Ultimately, the optimized greedy approach strikes the ideal balance between simplicity and efficiency. Sorting the costs array is both practical and feasible within the problem's constraints, allowing us to maximize the number of ice cream bars purchased while adhering to the budget. This strategy avoids the computational overhead of the brute force approach and the potential memory limitations of counting sort for larger ranges. By leveraging this method, we ensure clarity, maintain performance, and stay within acceptable resource limits, making it the most robust choice for solving this problem. In this problem, the objective is to determine the maximum number of ice cream bars that can be purchased within a fixed budget. Each bar has a specific cost, and our strategy is to prioritize buying the cheapest bars first to maximize the number purchased. This is a classic greedy algorithm approach. First, we start by parsing the input, which includes the costs array, representing the price of each ice cream bar, and the coins, which is the total budget available. For example, if we have costs equals 1, 3, 2, 4, 1, and coins equals 7, these represent the data we will work with. Next, we sort the costs array in ascending order. By sorting, we ensure that we can process the cheapest ice creams first, which is the most efficient way to use the budget. After sorting, the costs array becomes 1, 1, 2, 3, 4. This sorting operation has a time complexity of O, n asterisk log n, where n is the number of items in the costs array, but it is a necessary step for our greedy approach to work effectively. Now that the costs are sorted, we initialize two variables. The first is bars underscore purchased, which starts at 0 and keeps track of the number of ice cream bars we've bought so far. The second is remaining underscore budget, which is initially set to the total budget, or coins, and tracks how much money we have left as we make purchases. With these variables ready, we iterate through the sorted costs array. For each cost, if the current cost is less than or equal to the remaining underscore budget, we deduct it from remaining underscore budget and increment the bars underscore purchased counter. If we encounter a cost that exceeds the remaining underscore budget, we stop the loop early, as no further purchases are possible. For example, starting with remaining underscore budget equals 7 and bars underscore purchased equals 0, we buy the first bar for 1 coin, leaving remaining underscore budget equals 6 and bars underscore purchased equals 1. We buy the second bar, also for 1 coin, so remaining underscore budget equals 5 and bars underscore purchased equals 2. Then, we buy the third bar for 2 coins, reducing remaining underscore budget equals 3 and bars underscore purchased equals 3. The fourth bar costs 3 coins, which we can afford, so remaining underscore budget equals 0 and bars underscore purchased equals 4. The fifth bar costs 4 coins, which we cannot afford, so we stop here. After completing the iteration, the final step is to return the value of bars underscore purchased, which represents the maximum number of ice cream bars that can be bought. In the example we just walked through, the result is 4, as that's the maximum number of bars we could afford with the given budget. This approach works because of the greedy choice property. By always buying the cheapest available bars, we are making locally optimal choices that lead to a globally optimal solution. Sorting the costs upfront is a critical step that enables this strategy, even though it adds O, n asterisk log, n, complexity. Additionally, the algorithm is efficient in its use of the budget, as it stops processing as soon as the remaining budget is insufficient for the next bar. This early stopping mechanism ensures we don't waste time on unnecessary computations, making the approach scalable even for large inputs. To handle edge cases, we consider several scenarios. If the costs array is empty, no bars can be bought, so we return 0. Similarly, if all costs exceed the budget, it's impossible to buy any bars, and the result is also 0. If the budget itself, coins, is 0, there's no money available, so again, the result is 0. Beyond these special cases, the algorithm relies on the costs array in two variables, bars_purchase to track the number of bars bought and remaining_budget to keep track of the current budget after each purchase. These components ensure the algorithm remains simple and efficient while addressing various input scenarios. Analyzing the complexity, the time complexity of this algorithm is dominated by the sorting step, which takes O, n asterisk log n. The iteration through the sorted array takes O, n, so the total time complexity is O, n asterisk log n. The space complexity, on the other hand, is O, 1, in terms of additional space, as the sorting is done in place, and only a few variables are used. For optimizations, one potential improvement involves stopping the sorting early if a significant number of costs exceed the budget, as these items are irrelevant. Alternatively, a min-heap data structure could replace sorting to prioritize the cheapest items dynamically, but this would increase space complexity. Overall, the algorithm balances simplicity and efficiency, making it well-suited to solve the problem within the given constraints. This solution uses a greedy algorithm to solve the problem of maximizing the number of ice cream bars that can be purchased within a given budget. Here's the step-by-step explanation of the code. 1. Sorting the costs. The first step is to sort the list of costs in ascending order. This ensures that we prioritize purchasing the cheapest ice cream bars first, which is the key idea behind the greedy approach. 2. Variable initialization. We initialize a counter ice_cream_count to keep track of the number of ice cream bars purchased. Additionally, the coins variable represents the remaining budget. 3. Iterating through costs. Using a for loop, we iterate through the sorted list of ice cream costs. For each cost, if the remaining budget, coins, is greater than or equal to the current cost, we purchase the ice cream bar. This involves incrementing the ice_cream_count by 1 and reducing the budget, coins, by the cost of the ice cream. If the budget is insufficient to purchase the current ice cream, we break out of the loop since all subsequent costs are higher, due to the sorted order. 4. Returning the result. After exiting the loop, the ice_cream_count variable contains the maximum number of ice cream bars that can be purchased within the budget. This value is returned as the final result. This approach is efficient, with a time complexity of O, n log n, due to the sorting step, where n is the length of the costs list. The subsequent iteration through the sorted list has a linear time complexity of O, n, making the overall runtime dominated by the sorting step. The space complexity is O, 1, as no additional space proportional to the input size is used. This is the Java implementation of LeetCode problem number 1833, maximum ice cream bars. The logic mirrors the provided Python solution, using a greedy approach to buy the cheapest ice cream bars first. Java-specific features include type declarations, usage of arrays.sort for sorting, and an enhanced for loop for array traversal. The code is structured within the solution class and adheres to Java conventions for clarity and correctness. In this problem, we're tasked with determining the maximum number of ice cream bars we can buy given a list of their costs and a set amount of coins. The key idea is to maximize the number of ice creams purchased, which means prioritizing the cheaper options first. For example, if the costs are 1, 3, 2, 4, 1, and we have 7 coins, we can start by sorting the costs to get 1, 1, 2, 3, 4. Sorting helps us focus on the cheapest options first, ensuring we get the most bang for our buck. We initialize a counter ice_cream_count to 0 and start iterating through the sorted list, subtracting the cost of each ice cream from our available coins. For the first cost of 1, we have enough coins, so we buy it, increment the count to 1, and reduce the coins to 6. For the next cost of 1, we repeat the process, increasing the count to 2 and reducing the coins to 5. Continuing this way, we buy the next cheapest options, 2 and 3, until we run out of coins. At the end, we have purchased 4 ice creams, and the remaining coins are 0. Thus, the output for this example is 4 ice creams. For the next example, the costs are 10, 6, 8, 7, 7, 8, and we only have 5 coins. Sorting these costs gives 6, 7, 7, 8, 8, 10. Again, we initialize the ice_cream_count to 0 and begin iterating through the sorted list. However, the first cost is 6, which is greater than the coins we have. Since we can't afford even the cheapest option, we stop immediately. As a result, the total number of ice creams we can buy in this case is 0. This example shows how a lack of sufficient coins can prevent us from making any purchases, no matter the strategy. Now, consider the case where the costs are 1, 6, 3, 1, 2, 5, and we have 20 coins. After sorting, the costs become 1, 1, 2, 3, 5, 6. Starting with ice_cream_count at 0, we iterate through the sorted list. The first cost is 1, which we can afford, so we buy it, incrementing the count to 1 and reducing the coins to 19. The next cost is also 1, so we repeat the process, bringing the count to 2 and coins to 18. We then buy the next options 2, 3, 5, and 6, reducing the coins further after each purchase. By the end, we have bought 6 ice creams, and our remaining coins are 2. This example highlights how having more coins allows us to purchase more items, as we can afford both the cheaper and some of the more expensive options. The final output here is 6 ice creams. To summarize, the key to solving this problem lies in sorting the costs in ascending order. This ensures that we prioritize the cheapest options, maximizing the number of items we can buy. The approach is greedy because, at each step, we decide to buy an ice cream bar only if we have enough coins left. The process stops as soon as we encounter a cost that exceeds our remaining coins. This method is both efficient and effective, with a time complexity of O n log n, due to the sorting step, followed by an O n iteration through the costs. Together, these make the greedy approach optimal for solving the problem of maximizing the number of ice cream bars we can purchase. In analyzing the time complexity of the solution, we begin with the sorting of the ice cream costs. The costs.sort operation organizes the list in ascending order, and this sorting process is carried out using Python's timsort algorithm. Since timsort has a time complexity of O n log n, for a list of size n, this step is the most computationally expensive part of the algorithm. After sorting, the algorithm iterates through the sorted list to determine how many ice cream bars can be purchased with the available coins. In the worst-case scenario, this loop processes all n elements, contributing an O n complexity. However, when we combine these steps, the sorting operation dominates because O n log n grows faster than O n. As a result, the total time complexity of the solution is O n log n. Now, let's examine the space complexity of the solution. First, the input list costs already occupies O n space, where n is the number of ice cream bars. When it comes to sorting, Python's timsort algorithm is designed to perform in-place sorting, which ideally requires only O1 additional space. However, in the worst case, it may use up to O n temporary memory for certain operations, such as merging subarrays. Additionally, the algorithm employs a few auxiliary variables, like ice_cream_count and coins, which add only a constant O1 space. Taking all these factors into account, the total space complexity is dominated by the input storage and sorting overhead, resulting in O n. When comparing this optimized greedy approach to a naive or brute force method, the difference in efficiency becomes clear. A brute force approach would involve generating all possible subsets of the costs array and calculating their total cost to find the maximum number of ice cream bars that can be purchased. This approach has a time complexity of O2 to the power of n, as the number of subsets grows exponentially with the size of the array. Such complexity is impractical for larger inputs. In contrast, the current solution applies a greedy strategy, sorting the costs array and iterating through it, which drastically reduces the time complexity to O n log n. This optimization makes the algorithm scalable and efficient, even for larger datasets. Finally, let's analyze the best, average, and worst-case scenarios for the algorithm. In the best case, the costs array is already sorted in ascending order, and the available coins are sufficient to buy all the ice cream bars. Here, the sorting step still takes O n log n, while the iteration step adds O n, resulting in a total complexity of O n log n. In the average case, the algorithm follows the same process of sorting and iterating, leading to a consistent time complexity of O n log n. In the worst case, the costs array is unsorted, and only a few ice creams can be purchased. Even in this scenario, the sorting step dominates with O n log n, while the iteration contributes O n. Overall, the total complexity remains O n log n. This is mathematically justified because O n log n grows significantly faster than O n as n increases, making the additive term negligible. Similarly, the space complexity consistently stays at O n, accounting for the input storage and any temporary memory used during sorting. One of the most common mistakes when solving this problem is failing to sort the costs array. Without sorting, you may end up purchasing high-cost items early, which could exhaust your budget quickly and prevent you from maximizing the number of ice cream bars you can buy. By sorting the array in ascending order, you ensure that you prioritize cheaper items first, which is the foundation of an optimal greedy strategy. Another mistake is neglecting edge cases, such as when the costs array is empty, the budget is zero, or all items exceed the budget. These scenarios can lead to runtime errors or incorrect results, so it's important to handle them explicitly before diving into the main logic. Similarly, incorrect budget tracking can be problematic. If you forget to decrement the budget properly after each purchase, you could end up in an infinite loop or produce inaccurate results. To avoid this, make sure the budget is updated precisely after every purchase and include checks to ensure that the budget hasn't been exhausted. Lastly, avoid inefficient approaches like repeatedly using nested loops to find the cheapest item. This has a time complexity of O n squared, and is impractical for large inputs. Instead, sorting the array once and iterating through it in a single pass is far more efficient, with a time complexity of O n log n. Another issue to watch out for is misinterpreting the problem statement. If you misunderstand whether the goal is to maximize the number of items or minimize their cost, your solution might be completely off track. Carefully reading and understanding the problem's requirements and constraints is essential to avoid this pitfall. Now, from an interview perspective, this problem is a classic example of a greedy algorithm. Sorting the costs and iterating through them while tracking your budget is not only efficient but also demonstrates a clear understanding of how greedy algorithms work. Being able to explain why this approach guarantees the maximum number of items, for instance, by always choosing the cheapest items first, shows strong problem-solving skills. When discussing optimization, note that sorting the costs takes O n log n, which is acceptable for input sizes up to 100,000. Overcomplicating the solution with advanced data structures is unnecessary unless the interviewer explicitly asks for it. Additionally, make sure you can articulate how your solution handles edge cases, such as when no items are affordable or when the budget is so high that all items can be purchased. This demonstrates that your approach is robust and well thought out. To deepen your understanding of this problem, it's helpful to explore related problems that use similar greedy strategies. For example, LeetCode 135, Candy, involves a greedy allocation process with specific constraints, making it a great problem to practice. LeetCode 406, Queue reconstruction by height, is another greedy problem where sorting plays a key role in solving the challenge. LeetCode 1029, Two-City scheduling, focuses on cost minimization and also relies on a greedy approach for optimization. Finally, LeetCode 881, Boats to Save People, uses a combination of sorting and the two-pointer technique, which is also highly applicable to many greedy algorithm problems. Working through these problems can help reinforce the principles of greedy algorithms and improve your ability to apply them effectively in different scenarios. While the greedy algorithm is the most straightforward approach, there are alternative methods that can be useful in specific contexts. For instance, a heap-based approach involves using a min-heap to fetch the cheapest item without fully sorting the array. Building the heap takes O n, and each extraction operation is O log n, giving it a similar overall efficiency to sorting. However, this method can be slightly more complex to implement, and its primary advantage lies in avoiding the initial full array sorting. Another alternative is a dynamic programming approach, which uses a DP table to track the maximum number of items purchasable for each budget level. While this method might work for problems with additional constraints, its time complexity of O n asterisk budget makes it impractical for large budgets. Dynamic programming is generally not the best choice for this problem unless there's a significant twist in the requirements. Both approaches highlight the importance of choosing the right tool for the problem while keeping efficiency and clarity in mind. Great job! To recap, we used a greedy algorithm to solve the maximum ice cream bars problem efficiently. Remember to consider sorting and iterative methods for similar optimization problems. Thanks for watching, and don't forget to like and subscribe for more insightful solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!